Welcome to a journey through the deepest mysteries of reality itself. Tonight, we're exploring something that has haunted physicists for over a century. Something so profound that it forced even Einstein to question everything he believed about the universe. Picture this: the two most successful theories in the history of science, quantum mechanics and general relativity, theories that have given us computers, GPS satellites, and our understanding of black holes, cannot coexist. They are fundamentally, mathematically incompatible. This is the quantum gravity paradox, and it represents perhaps the greatest intellectual crisis in modern physics. I'm here to guide you through this labyrinth of ideas, this place where space and time themselves might dissolve into something far stranger than we've ever imagined. As we drift together through these concepts, let yourself settle into the mystery. There's no need to grasp every detail, no equations to memorize. Just allow these ideas to wash over you like waves, each one revealing another layer of the puzzle that continues to challenge our understanding of everything. Before we begin our descent into this beautiful paradox, I'd love to know where you're listening from tonight. Are you curled up in a quiet room, perhaps watching the stars through a window, wondering about the fabric of space itself? Or maybe you're in a bustling city, surrounded by the hum of technology that exists only because we've learned to dance with quantum mechanics, even though we don't fully understand its deepest secrets. Wherever you are, you're part of this story, because the mystery we're about to explore touches every atom in your body, every photon of light that reaches your eyes. But if you find these gentle explorations of reality's edge compelling, a like and subscribe helps more souls discover these quiet corners of wonder. And for those already traveling with us, thank you. Your presence makes this journey richer, more meaningful. The community we're building here is one of curious minds, people who aren't afraid to sit with big questions, to let mystery be mystery, while still reaching toward understanding. Now let's begin our exploration of the paradox that shattered certainty itself. To understand why quantum gravity represents such a profound challenge, we need to appreciate the extraordinary success of the two theories it seeks to unite. Think of modern physics as a cathedral built on two magnificent pillars, each so successful, so precisely tested that they've become the foundation for our entire technological civilization. The first pillar is quantum mechanics, that strange and wonderful theory that governs the behavior of atoms, electrons, and all the smallest constituents of matter. Quantum mechanics gave us semiconductors and lasers, MRI machines, and solar panels. It's the theory behind the device you're listening to this on right now. Every transistor in every computer operates according to quantum mechanical principles. The GPS satellite that guides you home works because we can predict the quantum behavior of atoms with breathtaking precision. But quantum mechanics is more than just a practical tool. It's a window into a reality far stranger than our everyday experience suggests. In the quantum world, particles exist in multiple states simultaneously until observed. They can tunnel through barriers that should be impossible to cross. They become entangled across vast distances, sharing fates in ways that Einstein famously called spooky action at a distance. This isn't science fiction or mystical speculation. These are measured, reproducible phenomena that form the bedrock of modern technology. The second pillar is Einstein's general relativity, his geometric theory of gravity. Where Newton saw gravity as a force pulling objects together, Einstein revealed it as the curvature of spacetime itself. Massive objects don't pull on each other through some mysterious action at a distance. Instead, they warp the very fabric of space and time, creating curves that other objects follow. It's as if the universe were a vast rubber sheet, and planets and stars create dimples and valleys that guide the motion of everything around them. General relativity has been tested with extraordinary precision. It predicted the bending of light around massive objects, the precession of Mercury's orbit, the existence of black holes and gravitational waves. When the LIGO detectors first heard the whisper of two black holes colliding 1 billion light-years away, they were listening to the symphony of curved space-time itself, exactly as Einstein had predicted a century earlier. These two theories are monuments to human understanding, each validated by countless experiments, each essential to our modern world. And yet, when physicists try to combine them to create a single theory that describes both quantum phenomena and gravity, the mathematics simply breaks down. The equations produce infinities where there should be finite answers. The very foundations of both theories seem to contradict each other at the most fundamental level. Imagine trying to write a play where the first act follows the rules of a romantic comedy, but the second act must be a noir thriller. Not just different in tone, but operating by fundamentally different rules about how cause and effect work, how time flows, how reality itself is structured. This is the situation physicists find themselves in when they try to unite quantum mechanics and general relativity. In quantum mechanics, the universe is fundamentally probabilistic. You cannot know both the position and momentum of a particle with perfect precision. Reality exists in superposition, with multiple possibilities coexisting until the moment of measurement collapses the quantum wave function into a single outcome. The quantum world is discrete, granular, built from indivisible packets of energy and action. General relativity, by contrast, describes a universe that is smooth, continuous, and deterministic. Space-time is a flowing manifold, infinitely divisible, where every event is connected to every other event through the precise geometry of curved space. Einstein's equations tell you exactly how matter curves space-time and how that curvature guides the motion of matter. There's no uncertainty principle here, no probabilistic wave functions, just the elegant dance of geometry and matter unfolding according to precise mathematical laws. The conflict runs deeper than mere mathematical incompatibility. These theories embody different philosophies about the nature of reality itself. Quantum mechanics suggests that the universe is fundamentally uncertain, that randomness and probability are woven into the very fabric of existence. General relativity insists that the universe is a clockwork of geometric precision, where every curve of space-time follows inexorably from the distribution of matter and energy. When you try to apply both theories to the same situation, such as the interior of a black hole or the first moments after the Big Bang, the contradictions become unavoidable. Quantum mechanics demands that space and time become uncertain, fluctuating foam-like at the smallest scales. General relativity requires that space-time remain a smooth, well-defined manifold. Quantum theory predicts that vacuum energy should curve space-time dramatically, but general relativity can't accommodate the enormous energy densities that quantum field theory calculates for empty space. There's a distance so small, a time so brief, and energy so intense that both quantum mechanics and general relativity simply give up trying to describe what happens there. This is the Planck scale, named after the physicist Max Planck, who first recognized its significance. The Planck length is about 10 to the negative 35th meters, a distance so tiny that if you could enlarge an atom to the size of the observable universe, the Planck length would still be smaller than a grain of sand. At this scale, the very concept of space and time as we understand them begins to break down. Quantum fluctuations become so violent that the geometry of space-time itself starts to bubble and foam, becoming as turbulent as the surface of boiling water. This is what John Wheeler called quantum foam, a description of reality at its most fundamental level that sounds more like poetry than physics. Take a moment to contemplate what this means. The smooth space-time of Einstein, the stage upon which all cosmic drama unfolds, might be nothing more than an illusion, an approximation that emerges only at larger scales. At the Planck scale, space and time might not be continuous at all, but rather made up of discrete, indivisible chunks, pixels of reality that dance and fluctuate according to quantum rules we don't yet understand. The Planck energy is equally staggering, about 10 to the power of 19 gigaelectron volts, energies that would require a particle accelerator larger than a galaxy to achieve. This means we cannot directly probe the Planck scale with any conceivable experiment. We are forced to rely on theoretical consistency and mathematical beauty to guide us into this realm, where our two most successful theories collapse into paradox. But the Planck scale isn't just an abstract theoretical concept. It represents the frontier where all our deepest questions about reality converge. What happened at the very first moment of the Big Bang? What lies at the centre of a black hole? How does consciousness emerge from matter? All of these mysteries seem to point toward physics at the Planck scale, toward a realm where quantum mechanics and general relativity must somehow find a way to coexist. In his later years, Einstein became consumed by what many considered an impossible dream: the quest for a unified field theory that would merge gravity and electromagnetism into a single, elegant description of reality. This wasn't merely an academic exercise for Einstein. He believed deeply that the universe must be comprehensible, that beneath the apparent complexity of natural phenomena, there must be simple, beautiful laws waiting to be discovered. For 30 years, from the 1920s until his death in 1955, Einstein pursued this vision with increasing isolation from the mainstream physics community. While younger physicists were exploring the strange new world of quantum mechanics, Einstein remained convinced that God does not play dice with the universe, that there must be a deeper, deterministic reality underlying the probabilistic facade of quantum theory. His approach was geometrical, inspired by the success of general relativity in describing gravity as the curvature of space-time. If gravity could be understood as geometry, Einstein reasoned, why not the other forces as well? Perhaps electromagnetism was also a manifestation of space-time curvature, just in dimensions we couldn't directly perceive. Einstein explored theories with 5 dimensions, with anti-symmetric tensors, with elaborate mathematical structures that could accommodate both gravity and electromagnetism in a single geometric framework. He worked with passionate dedication, filling notebooks with calculations, pursuing mathematical elegance with an almost mystical faith that beauty and truth must be connected. But Einstein's quest was doomed from the start, though not for the reasons his critics supposed. The problem wasn't that his mathematical approach was wrong, or that his intuition about geometric unification was misguided. The problem was that he was trying to unify a universe that was far richer and more complex than anyone in his time could have imagined. Einstein knew only of 2 fundamental forces: gravity and electromagnetism. He had no knowledge of the strong nuclear force that binds protons and neutrons in atomic nuclei, or the weak nuclear force that governs radioactive decay. He was trying to build a theory of everything while knowing only half of the fundamental interactions that shape reality. Even more fundamentally, Einstein was working before the full implications of quantum mechanics had been understood. He rejected the probabilistic interpretation of quantum theory, convinced that it must be an incomplete description of a deeper deterministic reality. But quantum mechanics wasn't just a mathematical formalism, it was revealing something profound about the nature of reality itself, something that any complete theory would have to accommodate. Perhaps nowhere is the conflict between quantum mechanics and general relativity more dramatic than in the paradox of black hole information. This puzzle, first articulated by Stephen Hawking in the 1970s, strikes at the heart of what we think we know about information, causality, and the fundamental nature of reality. According to general relativity, anything that falls into a black hole is lost forever, hidden behind the event horizon where not even light can escape. The information that describes the quantum state of that matter, its position, momentum, and all other properties, seems to vanish from the universe completely. But quantum mechanics forbids the destruction of information. This principle, called unitarity, is as fundamental to quantum theory as conservation of energy is to classical physics. Information can be scrambled, encoded in incredibly complex ways, but it can never be destroyed. The quantum state of any system must evolve in a way that preserves all the information it contains. Hawking discovered that black holes aren't completely black. Through a subtle quantum mechanical process, they emit radiation and slowly evaporate away. But this Hawking radiation appears to be completely random, carrying no information about what fell into the black hole. When the black hole finally evaporates completely, it seems as though all the information that fell in has been destroyed forever, violating one of the most basic principles of quantum mechanics. This creates a profound paradox. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and information somehow escapes from black holes in ways we don't understand. For decades, physicists have struggled with this puzzle, recognizing that its resolution might require a complete revolution in our understanding of space-time, quantum mechanics, or both. As you listen to this, notice how the paradox mirrors something deeper about the human condition. We are constantly losing information, forgetting experiences, watching memories fade into the background of consciousness. Yet we maintain a sense of continuous identity, as if some essential information about who we are persists even as the details change. Perhaps the black hole information paradox is teaching us something not just about physics, but about the nature of existence itself. Recent breakthroughs suggest that the information does escape, but through mechanisms so subtle and complex that they challenge our understanding of space and time themselves. The resolution seems to require that the interior of a black hole and its exterior are not separate regions of space, but rather different descriptions of the same quantum information, encoded in ways that transcend our classical notions of locality and causality. This is more than just an abstract puzzle for theoretical physicists. It's a window into the deepest structure of reality, a place where our most fundamental concepts about space, time, information, and causality are forced to evolve or break entirely. In the 1970s, a small group of physicists began exploring a radical idea. What if the fundamental constituents of reality weren't point particles, but tiny vibrating strings? This simple concept would grow into string theory, perhaps the most ambitious attempt ever made to unify quantum mechanics and general relativity into a single, comprehensive description of all natural phenomena. The appeal of string theory lies in its mathematical elegance and its promise of explaining not just how quantum mechanics and gravity can coexist, but why the universe has the specific forces and particles that we observe. In string theory, every particle is a different vibrational mode of the same fundamental string, like different notes played on a cosmic violin. The electron, the photon, the graviton that carries gravitational force all emerge as different harmonics in this symphony of vibrating strings. But string theory comes with a price that challenges our most basic assumptions about reality. These strings cannot vibrate in just the 3 spatial dimensions we experience. They require at least 9 spatial dimensions, and possibly as many as 11 dimensions in total. Where are these extra dimensions? String theorists propose that they are curled up so small that we cannot perceive them directly, hidden at every point in space, like invisible flowers blooming in dimensions our senses cannot access. This isn't merely a mathematical curiosity. If string theory is correct, then every point in the space around you, every location you've ever occupied, contains entire hidden universes of curled up dimensions, each with its own geometric structure that determines the fundamental properties of matter and energy. String theory has produced remarkable insights and mathematical connections that suggest it might be on the right track. It naturally incorporates gravity as a quantum mechanical phenomenon, resolving many of the mathematical inconsistencies that plague other approaches to quantum gravity. It predicts the existence of supersymmetry, a beautiful symmetry between matter and force particles that could help explain the hierarchy of forces in nature. Yet string theory remains frustratingly difficult to test experimentally. The energies required to directly detect strings are far beyond what any conceivable particle accelerator could achieve. The extra dimensions, if they exist, are so small that they might forever remain beyond direct observation. Critics argue that string theory has become more philosophy than physics, a beautiful mathematical structure that may have no connection to the physical world we inhabit. But perhaps this criticism misses the point. String theory has already transformed our understanding of quantum field theory, black hole physics, and the mathematical structure of space and time. Even if strings themselves are never directly observed, the insights generated by string theory continue to illuminate the deepest puzzles of quantum gravity. Take a breath and imagine what this could mean for you. If string theory is correct, then you are not just made of atoms and molecules, but of vibrating strings that extend into dimensions you cannot perceive. Your very existence is a symphony playing across hidden geometries, a dance of quantum vibrations that creates the illusion of solid matter from pure mathematical harmony. The journey toward understanding quantum gravity continues, with new insights emerging from the intersection of mathematics, philosophy, and our deepest intuitions about the nature of reality. But this is just the beginning of our exploration. In our next chapter, we'll dive deeper into the competing approaches to quantum gravity, the revolutionary experiments being designed to test these theories, and the profound implications that the resolution of this paradox might have for our understanding of consciousness, time, and existence itself. The mystery deepens, the questions multiply, and somewhere in the intersection of quantum mechanics and general relativity, the next great revolution in human understanding waits to be discovered. While string theorists have been weaving their mathematical tapestries across 11 dimensions, another group of physicists has taken a more conservative approach to the quantum gravity puzzle. They ask a simpler question: what if we don't need to revolutionize everything? What if we can solve the paradox by carefully, methodically applying the rules of quantum mechanics directly to Einstein's geometry of spacetime. This approach is called loop quantum gravity, and it represents perhaps the most direct assault on the quantum gravity problem. Rather than introducing exotic new dimensions or fundamental strings, loop quantum gravity takes Einstein's equations and quantum mechanics as given, then asks what happens when you apply quantum principles to the fabric of spacetime itself. The answer is both beautiful and startling. According to loop quantum gravity, space is not the smooth, continuous manifold that Einstein envisioned. Instead, it has a granular structure at the smallest scales, made up of discrete loops and nodes that weave together like an intricate cosmic fabric. Imagine zooming into what appears to be a smooth piece of cloth, only to discover that it's actually woven from countless tiny threads, each connected to its neighbours in a precise geometric pattern. In this picture, space itself has atoms, not atoms made of matter, but atoms of geometry, indivisible units, of area and volume that cannot be subdivided further. A single atom of area in this quantum geometry is about 1 Planck length squared, a region so small that all the atoms in the observable universe would fit into a space the size of a grain of sand. But here's where it becomes truly mind-bending. Time in loop quantum gravity is not fundamental. What we experience as the flow of time emerges from the way these geometric loops evolve and change their connections to one another. The theory contains no time variable in its basic equations. Instead, time is what happens when the quantum geometry of space transforms itself moment by moment, creating the illusion of temporal flow from pure geometric change. Take a moment to sit with this idea. The seconds ticking by as you listen to these words might not be fundamental features of reality, but rather emergent patterns in a deeper geometric dance, happening at scales far below the reach of any instrument we could ever build. Your experience of time might metaphorically echo the way quantum geometry evolves, though neuroscience and physics treat conscious time perception separately from quantum processes in ways that create the appearance of temporal passage. Loop quantum gravity makes specific predictions that distinguish it from other approaches to quantum gravity. It suggests that the Big Bang was not the beginning of time, but rather a big bounce where a previous contracting universe reached a minimum size and then began expanding again. The theory predicts that black holes don't have singularities at their centres, but rather quantum bridges that might connect to other regions of spacetime, or even other universes entirely. Perhaps one of the most fascinating aspects of the quantum gravity quest is how it has revealed the deeply human nature of scientific progress. What should be a purely objective search for truth has become entangled with academic politics, funding competitions, and something that can only be described as tribal loyalty. String theorists and loop quantum gravity researchers often attend separate conferences, publish in different journals, and speak what amount to different scientific languages. It's as if two groups of explorers searching for the same hidden treasure have decided that their maps are not just different but incompatible, and that admitting any value in the other approach would somehow diminish their own quest. This division has persisted for decades, with each community developing its own mathematical formalism, its own way of framing the fundamental questions, and its own criteria for what would constitute progress toward a solution. String theorists point to the mathematical elegance of their theory and its ability to incorporate all known forces in a single framework. Loop quantum gravity researchers emphasize their more conservative approach and their ability to make specific, testable predictions without requiring unobservable extra dimensions. The irony is profound. Both approaches are grappling with the same fundamental mystery. Both have generated important insights, and both may ultimately be describing different aspects of the same underlying reality. Yet the human tendency toward in-group loyalty and intellectual territorialism has created barriers that may have actually slowed progress toward understanding quantum gravity. Recently, however, a new generation of physicists has begun to bridge this divide. Younger researchers, less invested in the historical battles between different approaches, are beginning to find common ground and shared insights. They recognize that the quantum gravity problem may be too big, too fundamental to be solved by any single approach working in isolation. As you reflect on this, you might notice how this pattern appears in many areas of human endeavour. How often do we become so attached to our particular way of understanding something that we lose sight of the larger truth we're all trying to reach? The quantum gravity community's journey from division toward potential synthesis offers a lesson not just about physics, but about the very human challenge of holding multiple perspectives simultaneously while remaining open to unexpected connections. For decades, physicists assumed that quantum gravity effects would forever remain beyond experimental reach. The Planck scale seemed impossibly small, the required energies impossibly large. How could we ever hope to probe physics at scales where space-time itself becomes quantum and uncertain? But human ingenuity has a way of finding paths where none seem to exist. In recent years, physicists have devised increasingly clever ways to search for the subtle signatures of quantum gravity effects in phenomena we can actually observe. These experiments don't directly measure quantum space-time, but they look for the accumulated effects of quantum gravity over cosmic distances and times. One approach involves studying the propagation of light from distant gamma-ray bursts, cosmic explosions so energetic that they can be seen across billions of light years. If space-time has a granular structure at the Planck scale, then photons of different energies might travel at slightly different speeds through this quantum foam, arriving at Earth separated by tiny but measurable time differences. Other experiments search for modifications to particle behaviour that might arise from loop quantum gravity's discrete space-time structure. If space truly consists of quantum loops, then particles moving through this space might experience tiny deviations from the smooth trajectories predicted by classical physics. These deviations would be incredibly small, but modern precision instruments are approaching the sensitivity needed to detect them. Perhaps most intriguingly, some researchers are exploring whether the quantum nature of gravity might manifest in laboratory experiments with ultra-cold atoms or precision measurements of gravitational fields. The idea is that if gravity is fundamentally quantum mechanical, then there should be subtle correlations or interference effects that distinguish quantum gravity from classical general relativity. These experiments represent a remarkable achievement of human creativity and technical precision. We are attempting to measure effects that occur at scales smaller than atoms using devices built from trillions of atoms, like trying to study the texture of individual threads in a tapestry while standing on the other side of a football field. The results so far have been tantalizingly ambiguous. Some experiments hint at tiny deviations from classical predictions, while others set increasingly stringent limits on the size of quantum gravity effects. We are still in the early stages of what may be a decades-long experimental program to test our theories of quantum gravity against reality. One of the most revolutionary ideas to emerge from quantum gravity research is the holographic principle, a concept so strange that it challenges our most basic assumptions about the nature of space, matter, and information itself. The principle suggests that all the information contained in a volume of space can be encoded on its boundary, like a hologram that creates the illusion of three-dimensional depth from a two-dimensional surface. This isn't just a mathematical curiosity or a metaphorical way of thinking about information. The holographic principle emerged from serious attempts to understand the thermodynamics of black holes and has become a central organizing idea in theoretical physics. It suggests that what we experience as three-dimensional space might actually be a kind of projection from information encoded on a distant two-dimensional surface. Imagine that you are not actually inside a three-dimensional room, but rather a pattern of information on the walls of that room. Information so complex and detailed that it creates the complete illusion of three-dimensional existence. Every thought you think, every breath you take, every quantum interaction in your body would be encoded in this two-dimensional information, but you would experience it as fully three-dimensional life. The holographic principle emerged from studying black holes, those mysterious regions where gravity becomes so strong that not even light can escape. Stephen Hawking and Jacob Bekenstein discovered that black holes have temperature and entropy, and that their entropy is proportional not to their volume, but to the area of their event horizon. This suggested that all the information that falls into a black hole is somehow encoded on its two-dimensional boundary, rather than in its three-dimensional interior. This insight led physicists to wonder whether the same principle might apply more generally. Perhaps our entire three-dimensional universe is actually information encoded on a two-dimensional boundary, a cosmic hologram of unimaginable complexity and detail. The mathematics of string theory provides some support for this idea, suggesting specific ways that higher dimensional physics can be equivalent to lower dimensional information processing. The implications are staggering. If the holographic principle is correct, then the distinction between inside and outside, between observer and observed, might be far more subtle than we imagine. You might be simultaneously a three-dimensional being experiencing life in space and time, and a pattern of information encoded on some distant boundary that you can never directly perceive. This connects to deep questions about the nature of consciousness and experience. If your entire existence can be encoded as information on a two-dimensional surface, what does this say about the relationship between mind and matter, between subjective experience and objective reality? Are you experiencing a three-dimensional projection of two-dimensional information, or is the two-dimensional encoding itself creating the subjective sense of three-dimensional existence? Perhaps the most profound insight emerging from quantum gravity research is that space-time itself might not be fundamental. Just as temperature emerges from the average motion of countless molecules, and just as the flow of a river emerges from the behavior of individual water molecules, space-time might emerge from something deeper and more fundamental. This idea represents a complete reversal of how we normally think about physics. Usually, we imagine particles and fields existing within space-time, moving through a pre-existing stage of space and time. But quantum gravity suggests that space-time is not the stage, but rather part of the performance, something that emerges from the interactions of more fundamental entities. In some versions of string theory, space-time emerges from the entanglement structure of quantum information. Regions that are highly entangled correspond to nearby points in space-time, while regions with little entanglement are separated by large distances. The geometry of space and the flow of time arise from the pattern of quantum correlations among these fundamental information processing entities. Loop quantum gravity suggests that space-time emerges from the collective behavior of quantum geometric degrees of freedom. The loops are nodes that make up the fabric of quantum space. What we experience as smooth space-time is like the surface of a calm lake, which appears continuous from a distance but reveals its molecular structure when examined closely enough. Other approaches propose that space-time emerges from networks of quantum computation, from the dynamics of consciousness itself, or from mathematical structures so abstract that they exist in a realm beyond both mind and matter. While these ideas remain highly speculative, they all point toward the same revolutionary conclusion. Space-time is not the foundation of reality, but rather an emergent property of something far more subtle and fundamental. Take a breath and consider what this might mean for your own experience of existence. The solid ground beneath your feet, the air flowing through your lungs, the space that separates you from the stars. All of it might be emergent patterns in a deeper reality that operates by rules we are only beginning to glimpse. You are not just in space-time, you might be space-time, a localized pattern in the cosmic dance of quantum information that creates the illusion of separate existence while remaining fundamentally connected to everything else. Recent breakthroughs in understanding the black hole information paradox have revealed something extraordinary. Black holes might be the most powerful quantum computers in the universe. This insight has emerged from decades of careful analysis of how information behaves in the presence of extreme gravity, and it's reshaping our understanding of both black holes and quantum computation. When matter falls into a black hole, its information doesn't simply disappear. Instead, it becomes encoded in the quantum state of the black hole in an incredibly complex way. The black hole processes this information through quantum mechanical operations that scramble it beyond recognition, but preserve it nonetheless. The Hawking radiation that slowly evaporates the black hole carries this information back out, but in such a thoroughly encrypted form that it would take longer than the age of the universe to decode it. This process of information scrambling and recovery represents quantum computation on a cosmic scale. The black hole is performing calculations of unimaginable complexity, processing the quantum information of everything that falls into it according to the laws of quantum mechanics and general relativity. The event horizon becomes a kind of quantum processor, transforming input information through operations that push the boundaries of what's computationally possible. This perspective has led to remarkable insights about the relationship between information, computation, and gravity. It suggests that gravity itself might be an emergent property of quantum information processing, that the curvature of space-time arises from the way information is encoded and processed at quantum scales. Some physicists now propose that the universe itself is a vast quantum computer, with every particle interaction representing a computational operation, every quantum measurement a processing step in a cosmic calculation whose purpose we can barely imagine. In this view, the laws of physics are not just descriptions of how things behave, but actual computational algorithms running on the hardware of quantum spacetime. This isn't mere speculation. The mathematics of quantum error correction developed for practical quantum computers has provided crucial insights into how black holes preserve information. the same principles that allow quantum computers to maintain coherent quantum states in the presence of noise and interference, explain how black holes can scramble information beyond recognition while still preserving it perfectly. As we push deeper into the implications of quantum gravity, we encounter one of the most mind-expanding ideas in all of physics. The possibility that our universe is just one bubble in an infinite cosmic foam, one thread in an endless tapestry of realities with different laws of physics, different fundamental constants, different possibilities for the emergence of complexity in consciousness. This multiverse concept arises naturally from several approaches to quantum gravity. In eternal inflation models, the rapid expansion that occurred just after the Big Bang continues in other regions of space, constantly creating new bubble universes with randomly varying properties. In string theory, the enormous number of ways to curl up the extra dimensions creates a vast landscape of possible universes, each with its own set of physical laws. The many worlds interpretation of quantum mechanics suggests that every quantum measurement splits reality into multiple branches, creating an ever-growing tree of parallel universes where every possible outcome actually occurs. In some branches you chose differently this morning. In others, the fundamental constants of physics are slightly different, leading to universes where stars burn differently, where atoms form different elements, where the very possibility of complexity and life unfolds in radically different ways. These aren't just academic possibilities. If the multiverse exists, then somewhere in the infinite expanse of cosmic possibility, there are universes where quantum mechanics and general relativity are perfectly compatible from the start, where the quantum gravity paradox never arose because reality was structured differently from the beginning. There might be universes where consciousness plays a more direct role in shaping physical reality, where the observer effect in quantum mechanics extends to macroscopic scales. There could be realities where time flows backward, where cause and effect operate by different rules, where the very concept of existence takes forms we cannot imagine. But perhaps most remarkably, there might be universes where beings like yourself have solved the quantum gravity paradox, where the marriage of quantum mechanics and general relativity has revealed new technologies, new ways of understanding consciousness, new possibilities for existence that we can barely glimpse from our current vantage point. As you contemplate this possibility, notice how it reframes the significance of our own quest to understand quantum gravity. We are not just solving an abstract puzzle in theoretical physics. We are uncovering the deepest principles that govern reality itself, principles that might apply not just to our universe, but to the infinite web of possible universes that quantum gravity theory suggests might exist. The quest to understand quantum gravity is more than an academic exercise. It's a journey toward a fundamentally new understanding of what it means to exist, to be conscious, to participate in the unfolding of reality itself. The theories we've explored tonight suggest that the universe is far stranger, far more interconnected, and far more mysterious than our everyday experience suggests. If loop quantum gravity is correct, then you're made of discrete atoms of space and time, and your existence is a pattern in the quantum geometry that underlies all reality. If string theory is right, then you are a symphony of vibrations across hidden dimensions, a harmony that extends into realms of space that you can never directly perceive. The holographic principle suggests that you might be information encoded on a distant boundary, while the emergence of spacetime implies that the very stage of your existence arises from quantum processes operating at scales far below any possible observation. The black hole information paradox reveals that even the most extreme objects in the universe process information according to quantum mechanical rules, while the multiverse possibility suggests that your particular way of existing is just one thread in an infinite tapestry of possible realities. But perhaps the most profound implication of quantum gravity research is that it reveals the deep unity underlying apparent diversity. Quantum mechanics and general relativity, despite their apparent incompatibility, are both describing aspects of the same underlying reality. The quantum world of uncertainty and probability and Einstein's geometric universe of curved spacetime are like different languages describing the same ineffable truth about the nature of existence. This points towards something that mystics and philosophers have long suggested, that the apparent separateness of things, the boundaries between self and universe, between mind and matter, between observer and observed, might be constructs of limited perspective rather than fundamental features of reality. Quantum gravity doesn't just unify two theories of physics, it suggests a deeper unity that encompasses everything. The journey continues, and with each new insight, each theoretical breakthrough, each subtle experimental hint, we move closer to understanding not just how quantum mechanics and gravity can coexist, but what this means for consciousness, for existence, for the very nature of what it means to be real. The paradox that broke Einstein's theories is teaching us that reality is far more beautiful, far more mysterious, and far more interconnected than we ever dared imagine. And in that mystery, in that interconnection, we find not just the seeds of a new physics, but the possibility of a new way of understanding our place in the cosmic story that continues to unfold around us and through us, moment by moment, breath by breath, in the eternal dance between quantum possibility and relativistic certainty. Our exploration of quantum gravity concludes here, but the mystery continues to deepen with each passing day. If these ideas have stirred something in you, if they've opened new questions or cast familiar experiences in a different light, then you might find resonance in our previous journey into consciousness itself. In Is Consciousness the Final Reality, a theory that changes everything? We explored how the deepest puzzles of physics might be pointing toward mind as the fundamental constituent of reality, the observer whose presence makes the quantum world real. These mysteries are all connected, all part of the same cosmic story waiting to be told. As we venture deeper into the quantum gravity landscape, we encounter territories where even our most advanced theories begin to whisper rather than speak with certainty. These are the realms where black holes become laboratories, where information theory meets cosmic geometry, and where the very notion of what we call inside and outside begins to blur into something far more subtle and interconnected than our everyday intuition suggests. Recent breakthrough research has begun to illuminate the black hole information paradox in ways that would have seemed like science fiction just a decade ago. The work emerging from theoretical physics laboratories around the world suggests that when you peer deeply enough into the mathematics of black holes, you discover something remarkable. They might be the universe's most sophisticated quantum computers, processing information in ways that stretch our understanding of computation itself. Consider this. When matter falls past the event horizon of a black hole, classical general relativity tells us it's gone forever, swallowed into a region from which no information can ever escape. But quantum mechanics insists that information cannot be destroyed, that every quantum state must be preserved in some form, somewhere. This creates a fundamental tension that has puzzled physicists for nearly 50 years. The resolution that's emerging is both elegant and mind-bending. Rather than information being destroyed or simply escaping in some conventional sense, it appears to be processed through quantum operations so complex that the black hole essentially becomes a cosmic encryption device. The information that falls in gets thoroughly scrambled through quantum mechanical processes, then slowly released through Hawking radiation in a form so deeply encoded that it would take computational resources beyond anything we can imagine to decode it. But here's where the story takes an unexpected turn. This quantum scrambling process doesn't happen in isolation. Recent calculations suggest that black holes might be connected to their own exteriors in ways that transcend our usual notions of spatial separation. Through quantum entanglement operating on cosmic scales, the interior and exterior of a black hole might be different descriptions of the same underlying information, like two sides of a coin that appear separate but are fundamentally unified. This insight has profound implications beyond black hole physics. If the resolution of the information paradox requires us to think of seemingly separate regions of spacetime as different faces of the same quantum information, then perhaps our usual notions of locality, of here versus there, need to be reconsidered at the most fundamental level. Take a moment to let this settle. The idea that distant regions of space might be connected through invisible quantum correlations challenges not just our physics, but our basic intuition about what it means for things to be separate. The boundary between you and the rest of the universe might be far more porous, far more interconnected than you've ever imagined. Deep within the mathematical structure of loop quantum gravity lies a vision of reality that would make even the most imaginative science fiction writer pause in wonder. According to this theory, the smooth spacetime of Einstein's relativity is an illusion, like the apparently smooth surface of a photograph that reveals its pixelated structure when examined closely enough. In the loop quantum gravity picture, space is woven from quantum threads, discrete geometric relationships that connect at nodes to form a vast network extending throughout the cosmos. Each thread represents a quantum of area, each node a quantum of volume. The familiar three-dimensional space we navigate daily emerges from the statistical behavior of countless these quantum geometric elements, like the way the flowing surface of a river emerges from the collective motion of individual water molecules. But this isn't merely a matter of scale, like discovering that apparently smooth surfaces are made of atoms. The quantum geometry underlying space operates by fundamentally different rules than the classical geometry we experience. In quantum geometry, areas and volumes come in discrete, indivisible units. You cannot subdivide a quantum of area any further, just as you cannot have half a photon or a fraction of an electron's charge. This discreteness has profound consequences. It means that the infinite densities and zero-sized points that play classical general relativity, the mathematical singularities that appear at the centers of black holes and at the moment of the Big Bang, simply cannot exist in loop quantum gravity. The theory naturally provides a quantum cutoff that prevents these infinities from arising. According to loop quantum gravity, what we call the Big Bang was not the beginning of time, but rather a big bounce. The universe we observe today emerged from a previous cosmic epoch that had been contracting under gravity until it reached the minimum size allowed by quantum geometry, then rebounded into the expansion we observe today. The moment of maximum contraction was not a singularity, but a quantum transition, a phase change in the geometry of space itself. Similarly, The centers of black holes do not contain infinitely dense points, but rather regions where the quantum geometry of space creates bridges, connections that might lead to other parts of our universe, or even to other universes entirely. The event horizon becomes not a one-way membrane into oblivion, but a transition zone between different phases of quantum spacetime. As you contemplate this picture of reality, notice how it transforms the meaning of your own existence. If space itself is quantum, then every breath you take moves through discrete quantum geometry. Every step you take traverses connections in a vast network of quantum relationships that extend from your immediate vicinity to the furthest reaches of the cosmos. You are not simply in space, you're part of the quantum geometric structure that space itself is made of. While loop quantum gravity quantizes the geometry of Einstein's spacetime, string theory approaches the quantum gravity puzzle from an entirely different direction, one that requires us to expand our conception of space itself. In the string theory universe, the familiar three dimensions of space are just the visible part of a much larger geometric symphony playing out in realms we cannot directly perceive. Imagine a garden hose viewed from a great distance. It appears to be a one-dimensional line stretching across your field of view, but move closer and you discover that it has width and depth, that it's actually a three-dimensional object with an internal structure invisible from afar. String theory suggests that our three-dimensional space might be like that distant view of the garden hose, a simplified projection of a reality that extends into 6 or 7 additional spatial dimensions curled up so tightly that they remain hidden from direct observation. These extra dimensions are not merely mathematical abstractions. In string theory, they have specific geometric shapes, intricate structures called Calabi-Yau manifolds that determine the fundamental properties of matter and energy in our three-dimensional world. The mass of an electron, the strength of the electromagnetic force, the reason why neutrinos have such tiny masses, all of these features of our universe arise from the precise geometry of these hidden dimensions. But here's where string theory becomes truly extraordinary. There are an enormous number of ways to curl up these extra dimensions, possibly 10 to the power of 500 different geometric configurations, each giving rise to a universe with different physical laws. This creates what string theorists call the landscape, a vast space of possibilities where each point represents a different way reality could be structured. This landscape might not be merely hypothetical. In some versions of string theory combined with cosmic inflation, the early universe underwent such rapid expansion that different regions settled into different geometric configurations. This would create a cosmic patchwork where different domains of space operate by different physical laws, separated by boundaries we could never cross because the expansion of space itself prevents any signal from travelling between them. You exist in one particular patch of this cosmic landscape, a region where the hidden dimensions happen to curl up in exactly the right way to allow for the formation of atoms, stars, planets, and eventually conscious beings capable of contemplating the mystery of their own existence. In the vast majority of possible universes in the string theory landscape, the laws of physics would not permit such complexity to emerge. This raises profound questions about the nature of existence itself. Are you here because the fundamental constants happen to take values compatible with complexity? Or is there some deeper principle that guides the universe toward configurations capable of supporting consciousness? Some interpretations suggest that observer selection might play a role. You find yourself in a universe compatible with your existence precisely because you exist to observe it. Perhaps the most revolutionary insight emerging from quantum gravity research is the possibility that space-time itself is not fundamental, but rather emerges from something deeper and more abstract. Just as the temperature of a gas emerges from the average motion of its constituent molecules, space-time might emerge from the collective behaviour of more fundamental entities that exist in a realm beyond space and time as we understand them. This idea challenges our most basic assumptions about the nature of reality. We're accustomed to thinking of objects as existing within space-time, moving through a pre-existing framework of space and time. But what if space-time is not the stage upon which the cosmic drama unfolds, but rather part of the performance itself, emerging from the interactions of actors we cannot directly perceive? In some interpretations of string theory, space-time emerges from the entanglement structure of quantum information. Regions that are highly entangled correspond to nearby points in space-time, while regions with little entanglement are separated by large distances. The familiar geometry of space and the flow of time arise from the pattern of quantum correlations among these fundamental information processing entities. Other approaches suggest that space-time emerges from networks of quantum computation, where the basic entities of reality are not particles or strings, but rather computational processes. In this view, the laws of physics are not descriptions of how things behave, but actual algorithms running on the quantum hardware of reality itself. Every particle interaction becomes a computational operation, every quantum measurement a processing step in a cosmic calculation whose purpose we can barely begin to fathom. Loop quantum gravity proposes its own version of emergent spacetime, where the smooth continuum we experience arises from the collective behaviour of discrete quantum geometric degrees of freedom. The loops and nodes of quantum geometry interact according to quantum mechanical rules, creating patterns that, when viewed from sufficient distance, appear as the curved spacetime of Einstein's general relativity. But perhaps most intriguingly, some researchers are exploring the possibility that spacetime emerges from consciousness itself, or from some more fundamental principle, of which consciousness is one manifestation. This remains highly speculative, with no scientific consensus, but it points toward a vision of reality where mind and matter, observer and observed, are not separate entities, but different aspects of a deeper unity. Take a breath and consider what this might mean for your own experience. If space-time emerges from more fundamental relationships, then your existence is not just taking place within space and time, but participating in their very creation. Every moment of consciousness, every decision you make, every relationship you form might be contributing to the ongoing emergence of the space-time framework that makes existence possible. One of the most stunning insights to emerge from black hole physics is the holographic principle, an idea so profound that it has revolutionized how physicists think about the relationship between information, space, and reality itself. The principle suggests that all the information contained within any volume of space can be encoded on its boundary, like a hologram that creates the appearance of three-dimensional depth from a two-dimensional surface. This isn't merely a clever mathematical trick or a useful approximation. The holographic principle emerged from careful analysis of black hole thermodynamics and has become a central organizing principle in theoretical physics. It suggests that what we experience as three-dimensional reality might actually be a projection from information encoded on a distant two-dimensional surface that we can never directly observe. The principle first emerged from studying black holes, where Stephen Hawking and Jacob Bekenstein discovered that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This suggested that all the information that falls into a black hole is somehow encoded on its two-dimensional boundary rather than distributed throughout its three-dimensional interior. But the implications extend far beyond black holes. If the holographic principle is correct, then our entire observable universe might be a three-dimensional projection of information encoded on a two-dimensional cosmic horizon surrounding us. Every star you see, every planet, every galaxy, and every thought you think might be a manifestation of information processing occurring on this distant boundary. This creates a profound puzzle about the nature of existence itself. Are you a three-dimensional being experiencing life within space, or are you a pattern of information encoded on a two-dimensional surface, creating the subjective experience of three-dimensional existence through information processing so sophisticated that it generates the complete illusion of spatial depth? The mathematics of string theory provides specific mechanisms for how this holographic encoding might work. In the ADS/CFT correspondence, one of the most important discoveries in theoretical physics of the past few decades, a theory of quantum gravity in a curved spacetime with one set of dimensions is exactly equivalent to a quantum field theory without gravity operating on the boundary of that space with one fewer dimension. This isn't just a mathematical curiosity, it represents a fundamental duality in the structure of reality itself, suggesting that descriptions of physics in different numbers of dimensions can be completely equivalent. The boundary theory and the bulk theory are not approximations of each other. They are exact mathematical translations, like the same story told in different languages. If you enjoy drifting through these explorations without interruption, members get every episode 48 hours early, completely ad-free. You can join them whenever you feel ready. The holographic principle has practical implications for understanding quantum gravity. It provides a way to study quantum gravity in higher dimensions by analysing equivalent theories without gravity in lower dimensions, making previously intractable calculations possible. It has led to insights about quantum error correction, the nature of quantum entanglement, and the relationship between geometry and information theory. But perhaps most profoundly, the holographic principle challenges our intuitive notion of locality, of inside and outside, of self and environment. If all the information that describes your existence can be encoded on a distant boundary, then the separation between you and the rest of the universe becomes much more subtle than it appears. One of the most surprising connections to emerge from quantum gravity research is the relationship between black hole physics and quantum error correction, the field of study concerned with protecting quantum information from decoherence and noise. This connection has revealed something remarkable. The universe itself might employ error correction mechanisms to preserve information across cosmic scales and timescales. In quantum computing, error correction is essential because quantum states are extremely fragile. Any interaction with the environment can cause decoherence, destroying the delicate quantum superpositions that make quantum computation possible. Quantum error correction protocols encode logical quantum information across multiple physical qubits in such a way that errors in individual components can be detected and corrected without destroying the encoded information. Recent research has revealed that black holes appear to employ similar error correction mechanisms to preserve the information of matter that falls into them. The quantum state of the infalling matter becomes encoded across the many degrees of freedom of the black hole in such a way that even though individual quantum state has become scrambled beyond recognition, the total information content is preserved and can, in principle, be recovered from the Hawking radiation. This suggests that the universe itself might be employing quantum error correction on a cosmic scale. The information that describes the quantum state of every particle, every interaction, every moment of history might be encoded in redundant ways across the structure of space-time itself, protected against loss through mechanisms we are only beginning to understand. The implications extend beyond black hole physics. If space-time emerges from quantum information, as several approaches to quantum gravity suggest, then the stability of space-time itself might depend on error correction mechanisms operating at the Planck scale. The smooth, continuous space-time we experience might be an error-corrected approximation of more fundamental quantum information processing. Some researchers are exploring the possibility that consciousness itself might be related to these cosmic error correction mechanisms. This remains highly speculative, with no scientific consensus, but it raises intriguing questions about the relationship between information processing, error correction, and subjective experience. Consider the implications for your own existence. If the universe employs error correction to preserve information, then the pattern of information that constitutes your consciousness, your memories, your identity might be encoded in redundant ways across the fabric of reality itself. The continuity of your experience from moment to moment might depend on cosmic error correction mechanisms operating at scales far beyond anything you can directly perceive. At the heart of quantum mechanics lies one of the deepest mysteries in all of physics, the measurement problem. Why does the act of observation seem to collapse the quantum wave function, transforming a superposition of multiple possibilities into a single definite outcome? And what happens to this mysterious process when gravity enters the picture? In standard quantum mechanics, particles exist in superposition states, simultaneously occupying multiple positions or having multiple values for properties like spin, until the moment they are measured. The measurement appears to randomly select one outcome from the range of quantum possibilities, with probabilities determined by the wave function. But what constitutes a measurement? When exactly does the collapse occur? And why does classical reality emerge from quantum possibilities? These questions become even more puzzling when we consider gravity. If space-time itself is quantum mechanical, as theories of quantum gravity suggest, then what happens when a quantum superposition includes different configurations of space-time geometry? Can the very fabric of space and time exist in superposition states? And if so, what could possibly collapse such a superposition? Some interpretations of quantum gravity suggest that gravity itself might play a special role in the measurement process. The idea is that gravitational effects, unlike other forces, cannot be shielded or isolated. Every quantum superposition that involves different spatial configurations of matter creates slightly different gravitational fields, and these gravitational effects extend throughout the universe, creating an unavoidable connection between quantum systems and their environments. This gravitational decoherence might provide a natural mechanism for the emergence of classical reality from quantum possibilities. As quantum systems become entangled with the gravitational field, their quantum coherence is gradually lost, causing wave functions to effectively collapse without requiring any special measurement apparatus or conscious observer. Other approaches suggest the opposite, that consciousness might be required to collapse quantum superpositions, and that this process might involve gravitational effects operating at the interface between quantum mechanics and general relativity. This remains highly speculative, but it points toward the possibility that consciousness and gravity might be more intimately connected than we currently understand. Roger Penrose has proposed that consciousness might arise from quantum gravitational effects in microtubules within neurons, processes that operate at the boundary between quantum and classical physics. While this specific proposal remains controversial and lacks experimental support, it illustrates how quantum gravity might connect to the deepest mysteries of mind and consciousness. As you reflect on these possibilities, notice how the measurement problem touches on fundamental questions about the nature of reality and your place within it. If observation plays a role in collapsing quantum superpositions, then every moment of conscious awareness might be participating in the ongoing creation of classical reality from quantum possibilities. Among the various approaches to quantum gravity, one of the most direct and conceptually clear is causal dynamical triangulation, a method that attempts to construct spacetime from the ground up using discrete geometric building blocks. Rather than starting with smooth spacetime and trying to quantize it, or introducing exotic new dimensions and particles, this approach asks, what if we build spacetime piece by piece from fundamental geometric elements and see what emerges? The basic idea is elegantly simple. Take spacetime and divide it into tiny four-dimensional simplices, the four-dimensional equivalent of triangles. These simplices are glued together according to quantum mechanical rules, creating a discrete approximation to spacetime geometry. As you include more and more of these building blocks and let them interact according to the principles of quantum mechanics and general relativity, patterns begin to emerge. Remarkably, when physicists run computer simulations of this process, something beautiful happens. The random quantum fluctuations of discrete geometry average out to produce smooth four-dimensional spacetime with the properties we observe in our universe. Time emerges as a preferred direction, space expands in a way that resembles cosmic inflation, and the large-scale geometry matches what we see in astronomical observations. This approach reveals something profound about the nature of spacetime itself. The smooth continuum of Einstein's general relativity might not be fundamental, but rather a statistical emergent property that arises when enormous numbers of discrete quantum geometric elements interact according to simple rules. It's similar to how the smooth flow of a fluid emerges from the chaotic motion of countless individual molecules, each following simple laws of physics. Causal dynamical triangulation makes specific predictions that distinguish it from other approaches to quantum gravity. It suggests that spacetime has a fractal structure at small scales, with a dimension that changes depending on the scale at which you examine it. At very small scales, spacetime might be effectively two-dimensional, gradually transitioning to the familiar four dimensions we experience at larger scales. The theory also predicts that the expansion of the early universe should have proceeded differently than predicted by classical general relativity, with quantum geometric effects creating subtle but potentially observable signatures in the cosmic microwave background radiation. These predictions provide hope that we might eventually be able to test theories of quantum gravity through astronomical observations. Perhaps most intriguingly, causal dynamical triangulation suggests that the apparent flow of time might emerge from quantum geometric effects. In the discrete quantum regime, there is no fundamental distinction between time and space. The emergence of time as a special direction, the arrow of time that gives structure to our experience, arises from the way quantum geometric elements prefer to organize themselves into configurations that break the symmetry between space and time. Take a moment to contemplate what this means for your experience of existence. If time emerges from quantum geometry, then every moment of your conscious experience is participating in the ongoing creation of temporal structure from more fundamental geometric relationships. You are not just existing within time, you might be contributing to the very emergence of time itself through the quantum geometric processes that constitute your being. Just when physicists thought they were making progress on the black hole information paradox, a new puzzle emerged that has shaken the foundations of our understanding even more dramatically. The firewall paradox, proposed by physicists at the University of California, Santa Barbara, suggests that the resolution of the information paradox might require abandoning some of our most basic assumptions about the nature of space-time itself. The paradox arises from a careful analysis of what happens to quantum information as it approaches and crosses the event horizon of a black hole. According to general relativity, someone falling into a black hole should experience nothing special as they cross the event horizon. The equivalence principle, one of the foundational principles of Einstein's theory, says that freely falling observers don't feel the effects of gravity. They should pass through the event horizon smoothly, unaware that they've crossed this point of no return. But the information paradox resolution requires that information falling into the black hole becomes maximally entangled with the Hawking radiation being emitted by the black hole. This quantum entanglement, when analysed carefully, appears to create a paradox. The quantum state of matter crossing the event horizon cannot simultaneously be smooth for infalling observers and properly entangled with the outgoing radiation to preserve information. The resolution proposed by the firewall advocates is radical. There is no smooth passage through the event horizon. Instead, anyone approaching a black hole would encounter a firewall of high-energy particles just outside the event horizon, a wall of energy so intense that it would incinerate anything trying to pass through. This preserves the information paradox resolution, but completely abandons the equivalence principle that underlies general relativity. This creates a fundamental crisis in theoretical physics. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and the equivalence principle fails at event horizons, or there's some third possibility that requires abandoning other fundamental assumptions about the nature of space-time and quantum mechanics. Recent research has suggested various resolutions to the firewall paradox, each requiring subtle modifications to our understanding of space-time, information, or quantum mechanics. Some propose that the interior of the black hole is not a separate region of space, but rather the same region as the exterior, described from a different perspective. Others suggest that the firewall only appears for observers who have access to complete information about the quantum state of the black hole, information that might be impossible to gather in practice. The firewall paradox illustrates how quantum gravity research pushes us to the very limits of conceptual consistency. When we try to combine our best theories of quantum mechanics and gravity, we encounter paradoxes that force us to question our most basic assumptions about reality. The resolution of these paradoxes might require not just new mathematics, but new ways of thinking about existence itself. As you consider this paradox, notice how it reflects deeper questions about the nature of boundaries and transitions in your own experience. What happens at the boundary between conscious and unconscious, between self and other, between known and unknown? Perhaps the firewall paradox is teaching us something, not just about black holes, but about the nature of boundaries themselves in a quantum universe. While string theory and loop quantum gravity have dominated discussions of quantum gravity for decades, another approach has been quietly gaining momentum, offering a more conservative but potentially revolutionary path toward understanding how quantum mechanics and gravity can coexist. This approach, called asymptotic safety, suggests that gravity might be able to regulate its own quantum behavior through mechanisms that are already hidden within Einstein's equations. The basic idea of asymptotic safety is that while gravity appears to become uncontrollably strong at short distances, leading to the mathematical infinities that plague attempts to quantize it, there might be a special configuration where these infinities cancel out. This would create a fixed point in the behavior of quantum gravity, a configuration where the theory becomes mathematically well-behaved and predictive even at the Planck scale. This isn't just wishful thinking. Asymptotic safety has been demonstrated to work in simplified models, and increasingly sophisticated calculations suggest that it might work for full quantum gravity as well. The theory makes specific predictions about how the strength of gravity should change as you probe shorter and shorter distance scales, predictions that might eventually be testable through precision experiments or astronomical observations. What makes asymptotic safety particularly appealing is that it doesn't require exotic new dimensions, fundamental strings, or discrete spacetime geometry. Instead, it suggests that the key to quantum gravity lies in understanding the deep mathematical structure of Einstein's equations themselves, structure that becomes visible only when you push the theory to its absolute limits. If asymptotic safety is correct, then spacetime remains smooth and continuous even at the Planck scale, but with quantum fluctuations that are regulated by the theory's own internal consistency requirements. This would mean that the extreme conditions at the centres of black holes and during the first moments of the Big Bang are described by a natural extension of general relativity, not by fundamentally new physics. The approach also suggests that the apparent incompatibility between quantum mechanics and general relativity might be an artifact of applying these theories outside their natural domains of validity. Just as Newton's mechanics works perfectly well for everyday situations but requires modification at very high speeds or in strong gravitational fields, our current formulations of quantum mechanics and general relativity might simply need refinement rather than wholesale replacement. Asymptotic safety research has revealed unexpected connections between gravity and other fundamental forces, suggesting that all the forces of nature might be unified not through grand unifying principles that operate at the deepest level of reality, but through the self-regulating behaviour of spacetime itself at extreme scales. Recent calculations in asymptotic safety have revealed tantalising hints that this self-regulation might extend beyond gravity to encompass all the fundamental forces. The mathematical structures that allow gravity to remain finite at short distances bear striking resemblances to the structures that govern the strong nuclear force, electromagnetism, and the weak force. This suggests the possibility of a unified description of all forces not through exotic new physics, but through the deep mathematical harmony already present in the equations we use to describe nature. For decades, the study of quantum gravity seemed condemned to remain purely theoretical, forever beyond the reach of experimental verification. The energies required to directly probe the Planck scale are so enormous that they would require particle accelerators larger than solar systems. The effects of quantum gravity seem destined to remain hidden in mathematical equations rather than revealed through direct observation. But human ingenuity has a way of finding paths through seemingly impossible terrain. In recent years, physicists have devised increasingly subtle and sophisticated ways to search for the whispers of quantum gravity in phenomena we can actually observe and measure. These experiments don't probe quantum gravity directly, but they listen for its echoes in the cosmic symphony that surrounds us. One of the most promising approaches involves studying the propagation of light across cosmic distances. If space-time has a granular structure at the Planck scale, as several theories of quantum gravity predict, then photons of different energies might travel at slightly different speeds through this quantum foam. The effect would be incredibly tiny, but when accumulated over billions of years of travel from distant gamma-ray bursts, these tiny differences might become detectable. Imagine light as a collection of runners in a cosmic marathon, where the track itself has an almost imperceptible texture. Runners with different stride lengths might be affected differently by this texture, causing them to arrive at the finish line separated by tiny but measurable time intervals. The Fermi Gamma-ray Space Telescope and other instruments are now sensitive enough to detect these minute timing differences, providing our first direct glimpses into the quantum structure of space-time itself. Other experiments are probing quantum gravity through its effects on the fundamental constants of nature. Some theories predict that these constants might actually change slowly over cosmic time as the universe evolves, or that they might vary slightly from place to place if space-time has a complex quantum structure. By comparing the behavior of atomic transitions in distant galaxies with laboratory measurements, astronomers are beginning to place stringent limits on how much these fundamental constants can change. Perhaps most intriguingly, some researchers are exploring whether quantum gravity effects might be detectable in precision laboratory experiments. The idea is that if gravity is fundamentally quantum mechanical, then there should be subtle correlations or interference effects that distinguish quantum gravity from classical general relativity. These effects would be extraordinarily small, but modern technology is approaching the sensitivity needed to detect them. Take a moment to appreciate the profound audacity of these experiments. We are attempting to measure effects that occur at scales smaller than atoms using instruments built from trillions of atoms. It's like trying to study the weave of individual threads in a tapestry while standing on the other side of a continent, using only the faint shadows cast by fireflies. The results so far have been tantalizingly ambiguous. Some measurements hint at tiny deviations from classical predictions, while others set increasingly stringent limits on the size of quantum gravity effects. We are still in the early stages of what may be a decades-long experimental program to test our theories of quantum gravity against the subtle testimony of nature herself. As we venture deeper into the mysteries of quantum gravity, we encounter questions that stretch beyond physics into the realm of philosophy and consciousness itself. If quantum mechanics requires observers to collapse wave functions, and if gravity is quantum mechanical, then what role might consciousness play in the very structure of space-time? This remains one of the most speculative and controversial areas of quantum gravity research, with no scientific consensus on whether consciousness plays any special role in quantum mechanics, let alone in quantum gravity. But the questions are so fundamental, so closely tied to our understanding of what it means to exist and to be aware, that they cannot be entirely avoided. Some interpretations of quantum mechanics speculate that conscious observation could be linked to how quantum possibilities become definite outcomes, though this idea remains highly debated and not scientifically established. If such speculative interpretations were ever validated, they would raise questions about whether conscious observation has any indirect relationship to how quantum systems appear classical. Though current science does not confirm this is a speculative idea, not a proven scientific fact, but it points toward a vision of reality where mind and matter, observer and observed, are not separate entities but different aspects of a deeper unity. In this view, your conscious awareness may feel deeply connected to the universe you observe, but current science views this connection as experiential and interpretive, not as a direct influence on physical processes. Other approaches suggest that the relationship between consciousness and quantum gravity might be more subtle, rather than consciousness collapsing wave functions. It might be that certain types of quantum gravitational processes give rise to the kinds of information, integration, and processing that we associate with conscious awareness. Roger Penrose and Stuart Hameroff have proposed controversially that consciousness might arise from quantum gravitational effects in microtubules within neurons, processes that operate at the boundary between quantum and classical physics. While this specific proposal remains unproven and faces significant scientific skepticism, it illustrates how quantum gravity might connect to the deepest mysteries of mind and awareness. As you reflect on these possibilities, notice how they transform your relationship to the cosmos around you. If consciousness and quantum gravity are connected, even speculatively, then every moment of your aware presence connects you to the mystery of existence, though the fundamental physical processes shaping reality operate independently of human awareness. You would not be a passive observer of the universe, but an active participant in its ongoing creation. This doesn't mean that your thoughts directly control physical reality or that you can manifest changes in the world through mental effort alone. The connection between consciousness and quantum mechanics, if it exists at all, is likely far more subtle and complex than such simplistic interpretations suggest. But it does point toward a universe where awareness and physical reality are more intimately intertwined than our everyday experience suggests. One of the most profound implications of quantum gravity research is how it illuminates the relationship between simplicity and complexity, between the fundamental laws that govern the smallest scales and the rich, intricate structures that emerge at larger scales. The universe appears to be a vast system for generating complexity from simplicity, for creating intricate patterns and even consciousness itself from the interplay of basic quantum gravitational processes. Consider the journey from the quantum foam of the Planck scale to the emergence of galaxies, stars, planets, and life. At the deepest level, reality might consist of nothing more than quantum geometric relationships, discrete bits of area and volume interacting according to simple rules. Yet from these elementary interactions emerges the entire hierarchy of physical structures that make up our universe. Quantum gravity effects in the first moments after the Big Bang created tiny fluctuations in the density of matter and energy. These fluctuations, stretched to cosmic scales by inflation, became the seeds from which all large-scale structure in the universe would grow. Without the quantum nature of gravity, the universe would have remained perfectly smooth and featureless, incapable of supporting the complex structures needed for the emergence of life and consciousness. The process continues at every level. Quantum mechanics allows atoms to form stable structures despite the electromagnetic repulsion between their constituent particles. These atoms combine into molecules, which organize into cells, which develop into organisms, which evolve into beings capable of contemplating their own existence and the quantum gravitational processes that made that existence possible. This suggests a profound principle at work in the universe: the tendency for simple rules operating at fundamental scales to generate complexity and organization at larger scales. This emergence is not random or chaotic, but follows patterns and principles that we are only beginning to understand. The universe seems to be not just a collection of particles and forces, but a vast information processing system, constantly generating new patterns, new structures, new possibilities for organization and awareness. Some researchers speculate that this tendency toward complexity and organization might be more than just a happy accident. Perhaps the laws of physics themselves, including the principles that govern quantum gravity, are structured in such a way that they naturally give rise to complexity, information processing, and eventually consciousness. This remains a speculative idea with no scientific consensus, but it points toward a vision of the universe as fundamentally creative, constantly exploring new possibilities for structure and awareness. As you contemplate your place in this cosmic hierarchy of emergence, notice how you embody this principle in your own existence. You are made of atoms that obey quantum mechanical laws, organized into molecules that follow the principles of chemistry, arranged into cells that exhibit the properties of life, integrated into a nervous system that generates the phenomenon of consciousness. You are not separate from the universe's tendency toward complexity and organization. You are one of its most sophisticated expressions. One of the deepest mysteries in all of physics is the nature of time itself. Why does time seem to flow in only one direction? Why do we remember the past but not the future? Why does entropy increase, creating the thermodynamic arrow of time that gives structure to our experience? Quantum gravity research is beginning to illuminate these questions in ways that may fundamentally change our understanding of temporality itself. In the equations of fundamental physics, time is largely symmetric. The basic laws work equally well whether time flows forward or backward. Yet our experience of time is anything but symmetric. We age, memories form, causes precede effects, and the universe evolves from simple initial conditions toward increasing complexity and entropy. This asymmetry, the arrow of time, remains one of the most puzzling features of reality. Some approaches to quantum gravity suggest that the arrow of time might emerge from quantum gravitational effects operating at the Planck scale. In loop quantum gravity, time is not fundamental, but emerges from the way quantum geometric states evolve and change their relationships to one another. The direction of this evolution, the way quantum geometry prefers to unfold from one configuration to another, might create the fundamental arrow of time that underlies all other temporal asymmetries. Causal dynamical triangulation has revealed something remarkable in computer simulations. When quantum geometric building blocks are allowed to assemble themselves according to quantum mechanical rules, they naturally organize into structures where one dimension becomes time-like, while the others remain space-like. The emergence of time as a special direction appears to be spontaneous, arising from the quantum geometry itself, rather than being imposed from outside. This suggests a profound possibility that your experience of temporal flow, the sense that moments pass from past to future, might arise from the deepest level of quantum gravitational reality. Every tick of a clock, every heartbeat, every moment of conscious awareness might be participating in the fundamental quantum geometric processes that create the arrow of time itself. String theory offers its own insights into the nature of time. In some string theory models, time emerges from the entanglement structure of quantum information, with the direction of time corresponding to the direction of increasing entanglement entropy. As quantum systems become more entangled with their environments, they create the thermodynamic arrow of time that gives structure to macroscopic processes. But perhaps most intriguingly, some interpretations suggest that time might not be fundamental at all, but rather an emergent approximation that applies only at scales much larger than the Planck length. At the deepest level of reality, in the realm of quantum gravity, the concepts of before and after, cause and effect, might give way to more fundamental principles based on quantum information and geometric relationships. Take a breath and consider what this means for your moment-to-moment experience of existence. If time emerges from quantum gravity, then every instant of your conscious awareness is participating in the ongoing creation of temporality itself. You are not just existing within time, you might be contributing to the very emergence of time from more fundamental quantum gravitational processes. This doesn't mean that time is an illusion or that temporal relationships don't matter. Rather, it suggests that time, like space, might be an emergent property of deeper quantum gravitational reality, a pattern that arises from more fundamental processes and provides the framework within which complex structures like life and consciousness can unfold. While quantum gravity effects are most apparent at the smallest scales, recent research has revealed that they might have shaped the universe on the larger scales as well. The cosmic web, that vast network of galaxies and dark matter filaments that stretches across billions of light years, bears the subtle fingerprints of quantum gravitational processes that operated during the first moments after the Big Bang. The tiny quantum fluctuations in spacetime geometry that occurred during cosmic inflation were stretched to enormous scales, becoming the seeds from which all large-scale structure in the universe would eventually grow. These fluctuations, generated by quantum gravity effects operating at the Planck scale, determined where galaxies would form, how they would cluster together, and how the cosmic web would evolve over billions of years. In a very real sense, the quantum gravity processes that we struggle to understand in our laboratories have already conducted the ultimate experiment on cosmic scales. The distribution of galaxies we observe today is a fossil record of quantum gravitational effects operating under conditions of extreme energy and density that we could never reproduce on Earth. Modern astronomical surveys are beginning to decode this fossil record with unprecedented precision. By mapping the positions and velocities of millions of galaxies, astronomers can work backward to reconstruct the quantum fluctuations that gave rise to cosmic structure. These observations provide indirect but powerful tests of our theories of quantum gravity, allowing us to constrain models and distinguish between different approaches. The cosmic microwave background radiation, that faint glow left over from the Big Bang, carries even more detailed information about quantum gravitational processes in the early universe. The tiny temperature variations in this ancient light reflect quantum fluctuations in the geometry of spacetime itself, stretched and amplified by cosmic inflation into patterns we can observe and analyze. Some theories of quantum gravity make specific predictions about the statistical properties of these cosmic fluctuations. Loop quantum gravity suggests that the Big Bang was actually a big bounce, which might leave distinctive signatures in the cosmic microwave background. String theory predicts the existence of cosmic strings, topological defects in spacetime that could create observable patterns in the distribution of galaxies and the polarization of background radiation. As you gaze up at the night sky, perhaps on a clear evening when the Milky Way stretches across the heavens, you're looking at the end result of quantum gravitational processes that occurred when the universe was smaller than an atom. The pattern of stars you see, the structure of our galaxy, the vast web of cosmic architecture that surrounds us, all of it grew from quantum seeds planted by gravity itself during the universe's first moments. This connection between the smallest and largest scales in the universe reveals something profound about the nature of reality. The quantum and the cosmic are not separate realms, but different aspects of a unified whole. The same principles that govern the behavior of elementary particles also shape the distribution of galaxies across cosmic space and time. At the heart of many approaches to quantum gravity lies a deep connection between information theory and the geometry of spacetime. This connection, first glimpsed in the study of black hole thermodynamics, has grown into one of the most powerful organizing principles in theoretical physics, suggesting that information might be more fundamental than matter, energy, or even spacetime itself. The connection began with the realization that black holes have temperature and entropy, thermodynamic properties usually associated with collections of many particles rather than simple geometric objects. Jacob Bekenstein and Stephen Hawking discovered that the entropy of a black hole is proportional to the area of its event horizon, suggesting that the information content of everything that falls into a black hole becomes encoded on its two-dimensional boundary. This holographic encoding of information has profound implications for our understanding of spacetime itself. If all the information in a three-dimensional region can be encoded on its two-dimensional boundary, then perhaps the three-dimensional space we experience is itself a kind of holographic projection from more fundamental two-dimensional information processing. Recent advances in quantum information theory have revealed deep connections between entanglement, geometry, and the emergence of spacetime. Regions of space that are close together correspond to quantum states that are highly entangled, while distant regions correspond to states with little entanglement. The familiar geometry of space might emerge from the entanglement structure of more fundamental quantum information. This suggests a revolutionary possibility that spacetime geometry is not fundamental, but rather emerges from quantum information processing in much the same way that the behavior of gases emerges from the statistical mechanics of molecules. The curvature of spacetime around massive objects might reflect the way quantum information is processed and encoded in the presence of matter and energy. Loop quantum gravity provides its own perspective on the information geometry connection. In this approach, the discrete quantum states of geometry carry specific amounts of information, measured in terms of the areas and volumes they represent. The evolution of spacetime becomes a process of information transformation, where quantum geometric states change their relationships according to rules that preserve the total information content. String theory reveals yet another facet of this connection. In the ADS/CFT correspondence, a quantum gravity theory in higher dimensions is exactly equivalent to a quantum field theory without gravity in lower dimensions. This duality suggests that gravitational phenomena, including the curvature of spacetime and the formation of black holes, can be completely described in terms of information processing in a lower dimensional quantum system. As you consider these ideas, notice how they reframe your relationship to the physical world around you. If information is more fundamental than matter, then you are not just a collection of atoms and molecules, but a pattern of information processing that creates the experience of physical existence. Your thoughts, memories, and conscious awareness might be different aspects of the same information processing that gives rise to the space-time geometry you inhabit. This doesn't diminish the reality of your physical experience or reduce consciousness to mere computation. Rather, it suggests that the boundary between information and physics, between mind and matter, might be far more subtle and interconnected than our everyday experience suggests. As we push the boundaries of quantum gravity theory to their furthest limits, we encounter one of the most mind-expanding possibilities in all of physics: that our universe might be just one bubble in an infinite cosmic foam, one thread in an endless tapestry of realities with different laws of physics, different fundamental constants, different possibilities for the emergence of complexity and consciousness. This multiverse concept arises naturally from several approaches to quantum gravity, each suggesting different mechanisms by which multiple universes might come into existence. In eternal inflation models, the rapid expansion that occurred just after the Big Bang continues in other regions of space, constantly creating new bubble universes with randomly varying properties. Each bubble becomes a separate universe with its own laws of physics, its own fundamental constants, its own possibilities for structure and life. String theory's vast landscape of possible vacuum states suggests another route to the multiverse, with perhaps 10 to the power of 500 different ways to configure the extra dimensions required by string theory. Each configuration gives rise to a universe with different physical properties. The mass of the electron, the strength of gravity, the number of spatial dimensions, all of these features that we consider fixed might vary from universe to universe in this string theory multiverse. Loop quantum gravity offers its own version of cosmic multiplicity through the Big Bounce scenario. If our universe emerged from the collapse and rebound of a previous cosmic epoch, then this process might repeat indefinitely, creating an endless sequence of universes, each emerging from the quantum gravitational death of its predecessor. The many worlds interpretation of quantum mechanics, when combined with quantum gravity, suggests yet another form of multiverse. Every quantum event that could have multiple outcomes actually produces multiple outcomes, with reality constantly branching into parallel universes where every possibility is realized. In some branches, the fundamental constants are slightly different due to quantum fluctuations during inflation. In others, the development of complexity and consciousness takes radically different paths. But perhaps most remarkably, there might be universes where the quantum gravity paradox never arose, because the relationships between quantum mechanics and general relativity was structured differently from the beginning. There could be realities where gravity is naturally quantum mechanical, where the marriage of quantum principles and geometric spacetime creates no contradictions, no infinities, no conceptual puzzles. Take a moment to contemplate the implications of this cosmic multiplicity. If the multiverse exists, then somewhere in the infinite expanse of possibility, there are universes where beings like yourself have already solved the deepest mysteries of quantum gravity. There might be realities where consciousness plays a more direct role in shaping physical law, where the boundary between mind and matter is more porous than in our universe. This possibility reframes the significance of our own quest to understand quantum gravity. We are not just solving an abstract puzzle in theoretical physics. We are uncovering principles that might govern not just our reality, but the entire space of possible realities. The insights emerging from quantum gravity research might apply to universes we can never visit, realities we can never directly observe, but which might exist nonetheless in the vast symphony of cosmic possibility. As our exploration of quantum gravity draws toward its conclusion, we find ourselves contemplating the ultimate goal that has driven theoretical physicists for over a century. The dream of a final theory, a single mathematical framework that would unify all the forces of nature and explain the deepest principles governing reality itself. Einstein spent the last 30 years of his life pursuing this dream, seeking to merge gravity and electromagnetism into a unified geometric theory. His quest was premature, undertaken before the discovery of the strong and weak nuclear forces, before the full implications of quantum mechanics had been understood. But his vision of geometric unification continues to inspire physicists today. Modern approaches to quantum gravity represent the most ambitious attempts ever made to realize Einstein's dream of unification. String theory seeks to describe all forces and particles as different vibrational modes of fundamental strings, creating a single theoretical framework that encompasses quantum mechanics, general relativity, and all the forces of nature. Loop quantum gravity, while more conservative in its goals, provides insights into how gravity can be quantized without requiring exotic new dimensions or particles. Its success in resolving the mathematical infinities that plague other approaches to quantum gravity suggests that unification might emerge, not from adding new elements to our theories, but from understanding the deep mathematical structures already present in the equations we use to describe nature. The holographic principle suggests that this unification might be even more profound than previously imagined. If all the physics in any region of space can be encoded on its boundary, then perhaps the distinction between different forces, different particles, different aspects of reality is largely a matter of perspective. What appears as gravity in higher dimensions might be indistinguishable from electromagnetism or the nuclear forces when viewed from the appropriate holographic boundary. But the quest for unification raises profound questions about the nature of knowledge itself. Would a final theory actually represent the end of physics, or would it simply reveal deeper layers of mystery? Every answer in physics seems to generate new questions, every solution to open new puzzles. Perhaps the universe is constructed in such a way that complete understanding always remains just beyond our reach, not as a limitation, but as a feature that keeps reality eternally interesting. As you reflect on this possibility, notice how it mirrors patterns in your own experience of learning and understanding. Every insight you gain into yourself or your world seems to reveal new depths, new complexities, new questions to explore. Perhaps the quest for understanding, whether in physics or in life, is not about reaching a final destination, but about participating in an endless journey of discovery and wonder. The approaches to quantum gravity we've explored tonight represent humanity's most sophisticated attempts to understand the deepest principles governing reality. Whether any of them will ultimately succeed in their goal of unifying quantum mechanics and general relativity remains to be seen. But each has already transformed our understanding of space, time, matter, information, and consciousness in ways that will continue to influence human thought for generations to come. As we reach the end of our journey through the mysteries of quantum gravity, we return to a question that has threaded through our entire exploration. What is the relationship between consciousness and the fundamental structure of reality? This remains one of the most speculative and controversial areas of physics and philosophy, with no scientific consensus on whether consciousness plays any special role in quantum mechanics or quantum gravity. Yet the question persists because it touches on something essential about our existence. We are not just passive observers of the universe, we are part of it, patterns of matter and energy that have organized themselves into forms capable of contemplating their own nature. If quantum mechanics requires observers to collapse wave functions, and if space-time itself is quantum mechanical, then perhaps our conscious awareness participates in the ongoing creation of the reality we inhabit. This is a speculative idea, not a proven scientific fact, but it points toward a vision of existence where mind and matter, consciousness and cosmos are not separate entities but different aspects of a unified whole. In this view, your awareness is not separate from the quantum gravitational processes that shape space-time. It might be one of their most sophisticated expressions. Recent research in neuroscience has revealed that consciousness arises from the integrated information processing of neural networks, patterns of connection and communication that create unified experience from the activity of billions of individual neurons. Perhaps consciousness and quantum gravity operate by similar principles, both emerging from the integration of information across multiple scales and levels of organization. The holographic principle suggests that all the information in any region of space can be encoded on its boundary. If consciousness is viewed as information processing, some philosophical interpretations suggest metaphorical parallels with holographic principles. Though this is not a scientific claim about consciousness being encoded in space-time rather than localized in any particular region. This doesn't mean that your thoughts directly control quantum events, or that consciousness creates physical reality through some mystical process. The relationship between mind and quantum mechanics, if it exists at all, is likely far more subtle and complex than such interpretations suggest. But it does point toward a universe where awareness and physical reality are more intimately connected than our everyday experience reveals. As you sit with these ideas in the quiet of this moment, notice how they transform your relationship to the cosmos around you. If consciousness and quantum gravity are connected, then every moment of your aware presence connects you to the mystery of existence, though the fundamental physical processes shaping reality operate independently of human awareness. You would not be separate from the universe, but an integral part of its ongoing evolution, its constant exploration of new possibilities for structure, complexity, and understanding. The mysteries of quantum gravity continue to deepen with each new theoretical insight and experimental observation. The paradox that broke Einstein's theories has not yet been fully resolved, but our exploration of it has revealed vistas of possibility that Einstein himself could never have imagined. From the discrete geometry of loop quantum gravity to the extra dimensions of string theory, from the holographic encoding of information to the emergence of space-time itself, we have glimpsed a universe far stranger and more wonderful than our everyday experience suggests. Whether any of these approaches will ultimately succeed in unifying quantum mechanics and general relativity remains an open question. But the journey toward that unification has already transformed our understanding of reality in profound ways. It has shown us that the universe is not merely a collection of particles and forces following predetermined rules, but a creative, evolving system constantly exploring new possibilities for organization, complexity, and awareness. In the quiet spaces between what we know and what we wonder about, quantum gravity research has begun to illuminate questions that extend far beyond the realm of physics into the deepest mysteries of existence itself. The quest to unite quantum mechanics and general relativity has revealed that the universe operates by principles so subtle, so interconnected, that they challenge not just our scientific theories, but our fundamental assumptions about the nature of reality. Consider how this journey began with a simple observation. Two of our most successful theories cannot coexist in their current forms. What seemed like a technical problem in theoretical physics has blossomed into an exploration that touches on the nature of space and time, information and consciousness, causality and free will. The quantum gravity paradox has become a window into questions that philosophers have pondered for millennia, now illuminated by the precise language of mathematics and the careful methodology of experimental science. This convergence of physics and philosophy is not accidental. At the deepest levels of reality, the questions become inherently philosophical. When we ask what space-time is made of, we're also asking what it means for something to exist. When we explore how quantum measurements work, we're confronting the relationship between knowledge and reality. When we contemplate the emergence of classical space-time from quantum geometry, we're investigating the connection between appearance and underlying truth. The holographic principle suggests that what we experience as three-dimensional reality might be encoded on a two-dimensional boundary we can never directly perceive. This echoes ancient philosophical questions about the relationship between appearance and reality, between the world as we experience it and the world as it truly is. Plato's allegory of the cave, with its shadows on the wall representing imperfect reflections of true reality, finds unexpected resonance in modern physics. The measurement problem in quantum mechanics raises profound questions about the role of observation in shaping reality. While there is no scientific consensus that consciousness is required for quantum wave function collapse, the persistence of the measurement problem after nearly a century of investigation suggests that we may be missing something fundamental about the relationship between knowledge and existence. Take a breath and notice how these ideas invite you to examine your own relationship to reality. If the boundary between observer and observed is more subtle than classical physics suggested, then perhaps the boundary between yourself and the world around you is also more porous than everyday experience reveals. You are not separate from the quantum gravitational processes that shape space-time. You are one of their most sophisticated expressions. One of the most remarkable aspects of quantum gravity research is how it reveals the deep connections between phenomena occurring at vastly different scales. The quantum fluctuations that operate at distances smaller than atomic nuclei have shaped the distribution of galaxies across billions of light years. The discrete geometry that might exist at the Planck scale gives rise to the smooth space-time we experience in our daily lives. This dance of scales challenges our usual way of thinking about causation and influence. We're accustomed to the idea that small things are affected by large things, that the motion of planets influences tides on Earth, that the behaviour of ecosystems shapes the evolution of individual organisms. But quantum gravity reveals influences that flow in both directions, where the smallest scales of reality help determine the largest structures of the cosmos. The cosmic microwave background radiation, that faint glow left over from the Big Bang, carries the fingerprints of quantum gravitational processes that occurred when the universe was unimaginably small and dense. By studying this ancient light with increasingly sophisticated instruments, astronomers are effectively probing physics at the Planck scale, using the entire observable universe as a laboratory for testing theories of quantum gravity. This interconnection of scales suggests something profound about the nature of existence itself. There is no level of reality that operates in complete isolation from the others. The quantum realm influences the classical world, the microscopic shapes the macroscopic, the local connects to the cosmic through subtle but measurable effects that span the entire hierarchy of natural phenomena. String theory makes this interconnection explicit through its requirement for extra dimensions. The tiny curled-up spaces that exist at every point in our three-dimensional world determine the fundamental properties of matter and energy we observe. The geometry of these invisible dimensions shapes everything from the mass of particles to the strength of forces, creating an intimate connection between the unseen and the experienced. Loop quantum gravity reveals interconnection through its discrete geometric structure. The quantum loops and nodes that weave together to create space are not independent entities, but part of a vast network where each element influences its neighbours, which in turn influence their neighbours, creating patterns of correlation that extend across the entire fabric of spacetime. As you contemplate your place in this hierarchy of scales, notice how you embody this principle of interconnection. The quantum mechanical processes occurring in your cells influence your thoughts and emotions, which in turn affect your interactions with others, which ripple out through social networks and eventually influence the larger patterns of human civilization. You are not just made of quantum processes, you are a channel through which quantum influences flow into the macroscopic world. Perhaps the most revolutionary insight emerging from quantum gravity research is the possibility that information, rather than matter or energy, might be the most fundamental constituent of reality. This idea, still speculative and without scientific consensus, suggests that what we experience as physical existence might emerge from information processing occurring at scales and in ways we're only beginning to imagine. The concept began with the discovery that black holes have entropy proportional to the area of their event horizons rather than their volume. This suggested that all the information that falls into a black hole becomes encoded on its two-dimensional boundary, leading to the holographic principle and the idea that three-dimensional physics might be equivalent to two-dimensional information processing. Recent advances in quantum information theory have revealed deep connections between entanglement, computation, and the geometry of spacetime itself. Some interpretations suggest that the curvature of spacetime around massive objects might reflect the way quantum information is processed and encoded in the presence of matter and energy. The familiar three-dimensional space we inhabit might be an emergent property of more fundamental information processing occurring in ways we cannot directly observe. This information theoretic perspective on reality has profound implications for our understanding of consciousness and subjective experience. If physical reality emerges from information processing, Then perhaps consciousness, which also involves the integration and processing of information, is more fundamental than we previously imagined. This remains a highly speculative idea with no scientific proof, but it points toward a vision of reality where mind and matter are different aspects of the same underlying information processing. The quantum error correction mechanisms that appear to operate in black hole physics suggest that the universe itself might employ sophisticated information preservation strategies. The patterns of quantum information that constitute your memories, your personality, your conscious experience might be encoded redundantly across the fabric of space-time itself, protected against loss through mechanisms operating at the deepest levels of quantum gravity. Take a moment to consider what this might mean for the continuity of your existence. If you are fundamentally a pattern of information processing, then the boundary between your consciousness and the information processing that gives rise to space-time becomes much more subtle. You might not just exist within the universe, you might be part of the ongoing information processing that creates and sustains reality itself. While much of quantum gravity research remains theoretical, we are entering an era where increasingly sophisticated experiments are beginning to probe the boundary between quantum mechanics and general relativity. These experiments don't directly observe Planck scale physics, but they search for the subtle signatures of quantum gravitational effects in phenomena we can measure with extraordinary precision. The Laser Interferometer Gravitational Wave Observatory, LIGO, has opened an entirely new window into the universe by detecting ripples in space-time itself. These gravitational waves, predicted by Einstein over a century ago, carry information about some of the most extreme events in the cosmos: the collision of black holes, the merger of neutron stars, possibly even echoes from the Big Bang itself. Future gravitational wave detectors will be sensitive enough to probe quantum gravitational effects directly. They might detect the discrete nature of space-time predicted by loop quantum gravity, or the extra-dimensional signatures suggested by string theory. The gravitational waves from the early universe might carry information about cosmic inflation, quantum fluctuations in space-time geometry, and the fundamental structure of reality at its most basic level. Space-based experiments are beginning to test whether the fundamental constants of nature truly are constant, or whether they change slowly over cosmic time as predicted by some theories of quantum gravity. By comparing the behavior of atomic transitions in distant galaxies with precise laboratory measurements, astronomers are placing increasingly stringent limits on how much these constants can vary. Quantum optomechanics experiments are exploring whether quantum effects can be observed in increasingly large mechanical systems. These experiments might eventually probe the boundary between quantum and classical physics directly, testing whether consciousness or measurement plays any special role in quantum mechanics, and perhaps illuminating the relationship between quantum mechanics and gravity in laboratory settings. The James Webb Space Telescope and its successors will peer deeper into space and time than ever before, observing the first galaxies to form after the Big Bang. These observations will test our theories of cosmic inflation, dark matter, and dark energy, all of which are intimately connected to the quantum gravitational processes that shape the early universe. Here we are at the end of our journey through the quantum gravity paradox. Yet the mystery itself continues to unfold with each passing day. The theories we've explored tonight, from the discrete loops of quantum geometry to the vibrating strings across hidden dimensions, from the holographic encoding of reality to the emergence of space-time itself, all point toward the same profound truth. The universe is far more interconnected, far more mysterious, and far more beautiful than we ever dared imagine. Einstein's theories weren't truly broken by quantum mechanics, nor was quantum mechanics proven wrong by general relativity. Instead, their apparent incompatibility has become a doorway into deeper understanding, revealing that reality operates by principles so subtle and interconnected that they transcend the boundaries of any single theoretical framework. The paradox that seemed to shatter certainty has instead shown us that the universe is not a machine to be dissected, but a living symphony to be experienced and wondered at. Perhaps the most profound lesson from our exploration is that you are not separate from these cosmic processes, the quantum gravitational effects that shape space-time, the information processing that might underlie reality itself, the emergence of complexity from simplicity. All of this is not happening around you, but through you. You are not just in the universe. You are part of the universe reflecting on itself through human awareness, a poetic, not literal perspective, a localized pattern in the cosmic dance of quantum possibility and relativistic certainty. The quest to understand quantum gravity continues, and with it, our understanding of what it means to exist, to be aware, to participate in the ongoing creation of reality itself. Sweet dreams, and remember, even in sleep, the quantum foam beneath all existence hums quietly on.